Right, so today, I'm Mengsen, by the way. I just arrived at Stanford University. I'm with psychiatry. But all the work I'm going to show you today has been done in the Center for Complex System and Brain Sciences at Florida Atlantic University. So I'm going to talk about my obsession, that is how multiple agents can, through their simple interaction, form complex collective patterns. So a little bit outline of this is, first I will talk about what do I mean by complex systems, because everyone in complexity science means a different thing when they say complex systems. So everyone has their own story, their own origin, so I will tell you a little bit about what I think what complex system is to me. And then how does it relate to multi-agent coordination? What is it? And what are the relevant existing studies? And then I will show you a human experiment that I conducted that was designed to study the coordination between 8 people. And then I developed a model to capture the observed phenomenon in this experiment. And then I observed some really complex dynamics in the experiment, so I want to think a little bit theoretically about how I can really systematically characterize these dynamic patterns based on their topological properties. And then eventually I developed a method to actually quantify these dynamic patterns and detect the changes in the dynamic coordination patterns using topological data analysis. So first of all, what is complex systems? What is a complex system and how does it have anything to do with multi-agent coordination? So it started with undergraduate trauma. I was in medical school studying pharmaceutical science. These are all my undergraduate textbooks. Most of them are in Chinese, so you probably don't know what it is. But in short, it consists of a large piles of disciplines. So what really confused me was that, well, we're talking about one system that is called the human being. And what you have is a catalog of all the piecemeal informations locally on different spatial temporal scales. But none of these textbooks actually told me how is a human being work across all these spatial temporal scales together. So what exactly is the kind of complex system I'm interested in? So I really like this quote from Weddington's book of How Animals Develop. So he said, well, living animals are constantly on the move. And they are also made up of smaller elements that's called organs. And in all the organs, there is something going on all the time. And these organs are built out of cells, and there are always some chemical action and reactions in those cells. So he said 2 things about these kind of complex systems. One is they have multiple levels of description. They cannot necessarily be reduced to one or another. The second one is that they are highly dynamical on these multiple levels of descriptions. The question is, how does this kind of system emerge? So he went on saying that in living organisms, these dynamics are not isolated. They adjust to one another so that the right thing can be done at the right time and right place. So it's the way that we're so impressed with how these innumerable separate processes work together, we call animals organisms. And if there is a secret of life, it is here we must look for it. It's among the causes that brings about the arrangements of innumerable separate processes in a single harmonious living organisms. So here what we see is that how many components can work together to become one integrated system through coordination. So the key question is, what kind of law of coordination can integrate separate individuals in the collective, and the collective, on the other hand, can constrain the activity of these individuals to form complex systems. And a collective relative to one levels of description can be individuals relative to another levels of description. And indeed, if we think about the collective of living animals, we have social organisms. As after my painful years studying pharmaceutical science, I went on to study criminology and found out the same theme has been repeated in criminology. So I really like this quote from Cutlet. He said that society itself contains the germs of crime. It is the collective that is constraining the amount of crime that's happening in the society. Criminals, the individuals, are simply the instruments that carries them out. And Cohen said, and these criminal subcultures has emerged from the mutual exploration or joint action of individuals. And the crime sometimes is a formation that might not have been anticipated by any of the individuals. So the collective pattern is truly an emergent phenomenon on the group level. So the complex system that I'm interested in has both the characteristic of have multiple levels of description, they are dynamical, and they have emergent behavior at higher levels of description. So the fun part has been done. Now I think, oh, okay, I need to quantitatively study this stuff. What are the laws of coordination, and under what condition they can give rise to this kind of complex systems in principle? So, well, at first I need to think of a dynamical process that is general enough that it can transcend multiple levels of description. It's not substance specific, it's not level specific. So I chose rhythmic processes. Human has been fascinated by rhythmic coordination through all ages, from the motions of stars and to the heartbeats. So I want to review some of the major theories that exist before my study to give you an impression of where we are on studying the rhythmic coordination in relation to complex systems. So first of all, we talk about large-scale rhythmic coordination, and the key examples are synchronization of many fireflies in the forest, and the synchronization of heart cells and people clapping in the audience. So the classical model is the Kuramoto model. It describes how individuals are entrained by a collective rhythm. And the individuals here are coupled phase oscillators, theoretically. So what are phase oscillators? So it assumes that each individual whose dynamics is completely described by its phase. The phase of each individual is much like an arm on a clock. So where the arm is pointing indicates where's the phase of this particular oscillator. And also like a clock, the model entails multiple phase oscillators. Like the clock, there are multiple arms on the clock. But there's something that's different between the Kuramoto model and the clock, is that these oscillators are in fact coordinated, they're interacting. So to describe the collective behavior of these multiple individuals, we can take a vector mean of all these individual oscillators, and that gives us the collective oscillator. And when the system is in the disorder state, meaning they're spreading out around the circle, the collective oscillation is really weak. The amplitude of the collective oscillator is really small. So if their interaction is strong enough, these oscillators will align themselves together, and this is an orderly state, and correspondingly, the collective oscillator have a relatively large amplitude, indicated by the size of the length of the vector here. So mathematically speaking, the Kuramoto says that the rate of change of each individual oscillator is a function of its relative phase to other oscillators. So what this term is saying that every oscillator is attracted to another oscillator's phase. So they want to be aligned with each other. And how strong that feeling is dependent on the coupling strength between them. And how much they want to go on independently is determined by the natural frequency of the oscillators, meaning if they're not coupled, attracted to other oscillators, they will keep this omega I at their own pace. With some mathematical transformation, we can rewrite the system into this form. It means that every oscillator is essentially want to reduce its distance to the collective phase. It's this angle here, that they are entrained by the collective oscillator. So what is interesting about the system to many theorists is the transition between the disorder state to the order state. So we want the emergence of order. And this is dependent on a critical level of coupling strength and how much this coupling strength is needed for the system to become in order is depend on how dispersed this natural frequency of individual oscillators are. The problem is, I have with the model, is that this is order without complexity. Once they enter in this state, they are all aligned with each other. They are no longer separable processes. They are not doing anything different. But this model has been shown to capture a lot of empirical phenomena over the past 20 years. So what has been missing in the empirical experiments? So it turns out that in the past empirical experiments of large-scale coordination, people often only measure the collective amplitude. They never actually look too much into the micro-level dynamics of these oscillators. The reason is there are too many oscillators. It's not very easy to detailedly study every relations, relative phases in the system. So, well, people can study smaller scale, right? But when people study smaller scale rhythmic coordination, they turn to really small scale. Normally, it's less than 4 oscillators. And the most obvious examples are animal gaze patterns. An essential difference from the large-scale coordination, empirical study of large-scale coordination, we're focused on multiple possible coordination patterns. We don't just have one orderly state. We have multiple orderly states. For example, a walking dog. So if you look closely, you will find out that the front legs of these dogs are oscillating opposite to each other. This is antiphase. And the front and hind leg, both the black legs, they are oscillating in phase with each other. So it's traditionally synchronizing. But if the dog walks a little bit faster, at a certain point, you'll find out the phase relation between the front and hind leg will become antiphase. And if it goes faster, the relation between front legs will become synchronized rather than in antiphase. So for animal gaze, at least for dogs, we have multiple stable patterns that we can use for different functional needs. So unlike the RCO coordination, which only have one single order. And the example I'm going to show you in terms of modeling is the Haken-Kelso-Bunz model. Describes an empirically observed phenomenon between the coordination between 2 components. It can be 2 fingers, 2 legs, or 2 neuronal populations. So initially, this model was proposed to study bimanual coordination. So you can oscillate your finger in antiphase or in inphase, much like the dog's legs. So here, the collective pattern here is relative phase. It's the difference between the 2 oscillators that are coordinating. And it can be in phase, or they're aligned, or it can be antiphase when they're opposite to each other. Both of them are orderly states. So the interest, the major interest of studying this model and relevant empirical experiments is the transition between orderly state to orderly state. So this model describes the dynamics of relative phase between 2 oscillators, which looks rather familiar because this is also a function of the relative phase between 2 oscillators. And it is also dependent on the difference between the frequency difference of these 2 oscillators. And it depends on the coupling strength between the oscillators. But here, what is different is there is a second order coupling strength, this term here. This term turns out to be critical in reproducing the phenomenon observed in experiment of both antiphase and in-phase patterns are stable. This is a time series of the relative phase between 2 oscillators. It says that if the system starts near antiphase, the trajectory will go into antiphase and stay there. If the system starts near in-phase, it will go into in-phase and stay there. So whether the system is in phase or antiphase depends on initial condition what I started with. And there are important parameters here, as I said. If we manipulate these coupling strength of the system, in particular, if we manipulate how strong the second order term is relative to the first one, we will see if the coupling strength ratio is strong enough, you will have both attractors stable. That is a region of bistability. But if the ratio is small enough, this is a reverse axis. This side is small. Only the in-phase attractor is stable, that the system only has one stable state, or we can say it's monostable. Well, if we change the frequency difference between the system, we'll find out for small difference between these two oscillators, you will still have two stable states. And if we increase it further, the weaker antiphase pattern will disappear first and the system become monostable. And if we further increase the difference between two oscillators, you will find out the relative phase start running forward and non-stopping. But if you look closely, you will find that this relative phase actually dwell for a longer period of time near those older attractors that are near in-phase and antiphase. So we call this pattern metastable coordination. So I also have problem with this model. Why is that? It has complex behaviors, but it doesn't have multiple levels of description. I only have one variable. How can I have multiple levels of description? This is, by the way, the work of my PhD advisor. So I was like, oh, no, this is not good enough. So I decided I need a mini-scale experiment. So the reason is I want a system that's large enough so I can examine the dynamics on multiple levels of descriptions at the same time, but it's also not too big to study the micro-level dynamics. So I did this experiment that I call the human firefly experiment, for reasons will become apparent. So I designed a new paradigm where I asked subjects to come into the lab, 8 of them, and sit around a table. I give each of them a little touchpad that they can tap on. I will record their tappings. And I also give each of them an LED array with 8 lights. So the flashing of each light will reflect their own tapping in real time, or the taps of others in real time. Or I can substitute these lights with metronomes so I can manipulate how fast they're tapping and what's the initial phase they're at when they start to interact. So this allows me systematically manipulate the frequency of phase of individuals. And I can also manipulate the coupling through the network connectivity among them. So these are all critical variables that I've told you in the classical models of rhythmic coordination. And now I can really manipulate them systematically to elicit phenomenon of coordination behavior at different spatial temporal scales. So in the real experiment that I did, come on. Oh, no, that's too far. Okay. So in the human experiment I did, I collected data from 120 subjects for each trial. They were first paced for 10 seconds by metronomes. And then I removed the metronome, and they were allowed to interact with each other through the flashing of LEDs and touchpads for 50 seconds. Their task was to continue to tap at a metronome frequency during this 50-second period. They were not asked to intentionally coordinate with other people. So all the observations were spontaneous coordination. So this is a replay of a real trial where everyone was paced with the same metronome. So it looks like fireflies in the dark. But I said I want to manipulate the system such that it might have coordination at different scales. So I assigned the metronomes a little bit differently. So I assigned each 4-person the same metronome. So the people were labeled with the same color, were paced with the same metronome. And I manipulate the frequency difference between these two groups such that I can induce the segregation and integration between two frequency groups and observe what's happening on the intergroup level, intragroup level, and microdynamics. So first of all, I want to show you the dynamics observed, real dynamics observed in this experiment. I'm going to start with one particular dyadic relative phase. This is, remember, embedded in a larger group. So you will see this pair, subjects 3 and 4, their relative phase stuck at in phase for a very long time, about 30 seconds, before they switch to antiphase. So this I've shown you in early studies of small-scale coordination is a sign of bistability.
Can you tell us the instructions that you gave to for example, participants 3?
So remember, they were paced for 10 seconds by a metronome. So these two were paced by the same metronome of the same frequency. So when they see each other, they were supposed to imaginarily tap at particular, like say 1.5 hertz. And they were asked to maintain, keep tapping at 1.5 hertz while looking at the LED array. That's the only instruction. It's a very simple instruction.
Okay, so keep tapping at the same hertz, frequency.
Frequency. Yes, they were not instructed to do this. This is a spontaneous behavior. And so let's look at another pair. So this pair, after they started, they quickly go to inphase and dwell there for a while, but quickly escape from it and stop at inphase again the next time they pass by it. So I told you about this before. It is called metastable coordination. So they never stuck at any phase. They recurrently visit particular configurations. So, all these stuff that I've already talked about in small-scale coordination. So, we're done. I didn't find anything new, right? But if we look closer at the first relative phase, we'll find out that there's some bumps in this relative phase near the in-phase in a periodic fashion. So I was thinking, well, why is that? Why are there bumps in this? We've never observed this in dyadic interaction. So you may have guessed it that these are from the same trial. It turns out that every bump in the yellow relative phase follows right after a dwells in the pink relative phase. What essentially says that every time that the person 1 is coming close to person 3 in phase, it causes a perturbation on the relation between 3 and 4. Or metaphorically, I said, me and my boyfriend has been in a long-term relationship at in phase, but there's another girl that keep calling him 3 times. Every time is longer than the previous one, and that creates some perturbation on my relationship with my boyfriend. Eventually, I was so pissed off, I flipped to antiphase with him. So more is different in a social sense. Multiple agents, interacting agents, give rise to multiple relations, and these relations go to compete with each other and give rise to emergent behavior that has not been observed in dyads alone. You might also have observed that none of these relations are actually totally stable. They simply dwell at different time scales. One is longer, the other is shorter, but recurrent. When we have more relations in the system, we will have even more different time scales involved in the dynamics. And the result is that the system will switch between different spatial patterns in a complicated way, which we will return to at a later time. What does it mean? But for now, in aggregates, if I plot the distribution of a relative phase between all the dyads in the group, I will find out that there is a strong in-phase peak at 0, and there's a very small antiphase peak at pi. And both of these peaks are decreasing with the diversity that I introduced in these groups, and the antiphase was the first to go. And on the microscopic level, I told you I manipulate the frequency difference between these groups. At the largest difference between groups, we see, now this is a frequency dynamics of these these 8 persons. You can see that the ensembles is clearly differentiated into a frequency group at around 2 hertz and another frequency group around 1.2 hertz. Well, if we decrease the difference between the 2 groups, you can still see there are one group at higher frequency, the other group at lower frequency, but there are much more interaction between them. And at either lower, if there is no frequency difference that I input into the system, they just form one supergroup. To quantify this, I studied a relation between all the dyadic couplings within groups and how it relates to dyadic couplings between groups. For example, when there's no frequency difference, if the coordination within group increase, it will correspond to a similar increase in intergroup coordination. I defined that the slope of this regression line is the levels of integration between 2 groups. I said if the slope is positive, meaning if more within group coordination give rise to more intergroup coordination, the two groups are more or less integrated. And this is a case for both low and intermediate diversity. And if the slope is negative, as for the case of high levels of diversity, it means that more intragroup coordination leads to less intergroup coordination. It leads to segregation. So I can say, well, what is the critical levels of diversity that differentiate the regime of integration and segregation? I can interpolate and find out is about 0.5 Hertz. And if I only look at the dynamics within these groups, remember I only manipulate the difference between groups, but I want to study if the outside changed the inside of the groups. And in fact, it did. So when there are more intergroup differences, you have a different group out there, it reduces your cohesion within the group. So just to summarize, I showed you in multi-agent case how metastability can give rise to spatiotemporal metastability. It means the group will switch between different complex spatial patterns sequentially. And on the dyadic level, I showed you there are strong inphase tendencies and weak antiphase tendencies. And I also showed you some results at the intergroup level and intragroup level. So now I want to model these phenomena mathematically. So what I want to do is the simplest model possible to capture three important quantitative results that I observed in dyadic level, intragroup level, and intergroup level. And after some tinkering around, I found out the simplest model that can reproduce all this phenomenon on multiple levels of descriptions take this form. It says the dynamics of individual oscillators is a function of their relative phase, non-surprisingly, and it depends on a coupling strength of the first order coupling and the strength of the second order coupling. So you should think this is rather familiar because if I remove the second order coupling, this is simply the Kuramoto model that I showed you earlier. If I set the number of oscillators n to 2, then it will derive the extended HKB model for small scale coordination. So this is a result, comparison between human behavior and model behavior for intergroup relation, which are reflected by the slope of these regression lines. And we also were able to reproduce the reduction of intragroup coordination due to the presence of intergroup difference. And on the dyadic level, the model showed both in-phase and antiphase peaks, and these peaks are reducing their amplitude with the increasing diversity. So, well, my committee member at the time asked me, well, if you can just use Kuramoto model to get the same results, why not use Kuramoto model because it's more famous, right? So I said, okay, I will try it. So it turns out that if I use the Kuramoto model, it will give me a really fat in-phase peak, and there will be a trough at antiphase. And it turns out that to reproduce the empirically observed phenomenon, you cannot get rid of the second order coupling. So the question is, what does it do? What does it tell us about coordination in complex systems? So it turns out that the ratio between, so how big the second order coupling relative to the first order coupling would determine whether the system is mono or multistable. So there is a critical coupling ratio such that if the coupling ratio is below 1, the system only have all in-phase states. This is a monostable system. And if the coupling ratio is greater than the critical value, the system can stay at any combinations of in-phase and antiphase. So the number of stable states is actually 2 to the n, where n is the numbers of oscillators. It means that a system's complexity, so the amount of possible behavior, will grow exponentially with the size of the system. Well, if you have a monostable system, the complexity of the system does not grow at all when the system grows. And this critical ratio itself that differentiates the domain of no complexity and complexity is actually invariant across scales. So it, in this sense, connects the emergence of complexity across scales. So to summarize, I showed you a model that captures experimental phenomenon at multiple levels of description. And it reconciled to well-studied models of large and small scale coordination. And I also show that the critical coupling ratio can connect the emergence and growth of the behavioral complexity of the system across scales. So now, time to wake up. I told you earlier that these systems exhibit spatiotemporal metastability. It means they switch from different spatial patterns sequentially. One question we can ask is, are these just random noise? Maybe they're just, switching randomly from one pattern to another. There is really nothing funny about it. So I will show you a systematic way to look at these patterns from a topological way. So first of all, we want to start with a simpler case. Let's say there are only two oscillators. When there are only two oscillators, their relation can be described by a single relative phase which leads on a circle. And if there are they stays in the fixed point, it takes a topology of a point on this circle. However, if the system became metastable, it starts wrapping around the circle. It takes a topology of the circle, which is the topology of the space itself. And there's only one type of metastable pattern, topologically speaking, which is constrained by the underlying space of two oscillator problems. Well, if we go into the coordination between three oscillators, we can characterize the relation between three oscillators with two relative phases. So 3, 2 relations. And we can plot, I would say, the location around the large circle on the torus indicate the value of one relative phase. And the location around the small circle represent the value of another relative phase in this triadic coordination. So now I say, well, I want to do a thought experiment. I said, what if, think of a 3 oscillator system. If one oscillator is naturally at 0 hertz, the other one at 1 hertz, and I have a third oscillator. If this oscillator has the same frequency with the first oscillator, they will become synchronized and they may coordinate metastably with the second oscillator. This will give us a simple topology of a large circle on the torus, meaning here the relative phase between lambda and oscillator at 0 is constant over time. Yes?
You have an oscillator at 0?
It's a relative phase. Remember, it's 3 oscillators. They're moving at different frequencies, and I'm talking about relative phase. Yeah, because right now I set these 2 oscillators to have the same intrinsic frequency, so they're just stuck together at 0 phase. And symmetrically, if I made this oscillator the same as a Boole oscillator here, this system will simply circle around the small circle here. Here, the relative phase between oscillator at 1 hertz and oscillator at lambda hertz will become constant. What was puzzling to me is that you cannot actually deform this loop continuously into this one because they are topologically non-equivalent. So the question is, how can two topologically distinct loops can change into each other under a continuous change of the parameter lambda, natural frequency of the third oscillator? So I did some numerical experiments. So I choose the coupling strands to be small enough such that the 3 oscillators are not synchronized at any moment in time. And I also want to quantitatively talk about these dynamic patterns. So I assign them some winding numbers. The winding numbers means that here 0, 1 means this pattern circle around the large circle for 0 times while it circles around the small circle for 1 times. And symmetrically, I can assign this pattern a number 1, 0. So the first thing I observe is for a wide range of change of the third oscillator, the variable oscillator, the topology itself of the pattern does not change at all. Even though the curve has been deformed and shifted, it assumes the same topology. And this topological information can also be seen in their frequency dynamics in terms of the clustering of the black line with the blue or the red line here. These are what I call the partial metastable coordination patterns because there are still two oscillators are more or less synchronized. These two oscillators, the blue and black here, they are not metastable. So this is a partially metastable pattern. The question is, can we find purely metastable pattern where none of the oscillators are synchronized? Yes, indeed. We can find in between that this pattern of type 1,1, meaning as one relative phase goes through 2 pi, the other relative phase also go through 2 pi, and gives you a symmetric pattern in the frequency dynamics. I call these purely metastable patterns. There is an interesting thing in the relation between the patterns and the relation between the numbers. If you look closely, if I add these two numbers together, two tuples together, you will get 1, 1 in the middle. And you happen to be able to find this pattern of type 1, 1 between the corresponding frequency parameter. So I said, well, can we reproduce this relation? And indeed, if we say we add these two topological type together, we should be able to find some patterns between these two that's of the type 1, 2. And we can find this pattern indeed, and it looks very much like the concatenation between this pattern and this pattern. And in the frequency dynamics, you can see this is a concatenation in time of one period of the pattern above and one period of the pattern below. Symmetrically so for the other case, when the oscillator 3 is closer to the lower oscillator. So there are multiple metastable patterns. And before I left, I was working with a mathematician. We were trying to study how there are infinitely many possible patterns emerging between these two values. So these patterns have never been observed in dyadic coordination. So these are really truly emergent complex order phenomenon coming out of just 3 oscillators. And more interestingly, we can categorize or think about them systematically in terms of relation between their topological types. So I have shown you that triadic example, very simple model of 3 oscillators, demonstrate the power of when we combine metastable coordination that's initially observed in dyadic interaction. When we add more relation into the system, we can generate infinitely many complex coordination patterns. And I give a topological way, preliminary way at least, to think about these patterns systematically. And the next step was really to say, well, in real data, how do we analyze these patterns? We don't have a priori knowledge about the mechanism that's generating these patterns. So I first want to tell you what's the difficulty in analyzing the real data in terms of real dynamics. So this is a boyfriend-girlfriend example that I showed you earlier. This is a rather simple, simply visualizable trial where you can see the system repeatedly visited a same pattern, meaning everyone was in phase for 3 times between 10 seconds and 40 seconds. And before that, they were doing something else. After that, they were doing something else. You can see this information because there are not many agents. And all these relative phases are relatively close in the time scale at which they evolve. Well, if we go to 8 people, we can describe them by 7 different relative phases. You can immediately see it's a little bit of a headache. The reason is, first of all, there are too many relations. And they also evolve on very different time scales. So the flatter one, I thickened the flatter lines. They're evolving on slower time scales. And in the background, there are steeper lines that are evolving in the much faster time scales. Well, even if I plot these mass on the separate axes, I split to 7 different axes, you still wouldn't be able to tell how these dyadic relations are actually forming a global structure. So I turn to a very traditional way of visualizing high-dimensional dynamical system that's called a recurrence plot. So this is a recurrence plot of the triadic example. So a recurrence plot, the color here, indicates how similar the state of a system at one point, 20 seconds, is similar to the state of a system at another time point, for example, 25 seconds. So here you can see a grid of 3x3 grid that represents the 3 recurrence of the same pattern that we observe in the dynamics. And before and after, it was something relatively different. So, well, okay, it tells us nothing new. Can it help us with this 8-person example? I'm not sure. It looks like as much a mess as before when I just show you all these squiggly curves. So we need some new tools to deal with these dynamics that are highly complex. So I have an idea. What about when we're having the original dynamics, I do not study the recurrence of the state variable themselves or the relative phase themselves. Instead, I analyze some topological features in these dynamics and construct some topological portrait of the dynamic patterns. And I study the recurrence of those topological features instead. So why does topology matter here? Well, I showed you a little bit theoretically before. But here I want to talk a little bit more generally about multi-scale structure, which I'm highly interested in, and how can we understand multi-scale structures with topology. And this figure you should see that in many places, in psychology article, etc. People will ask you, well, is this a B or is this many A's? Well, in fact, it's both. At one scale, you can see this, at finer scale, you can say there's many A's, and at larger scale, you can say this is one B. So the description of the system is scale dependent, much like living systems. Well, how can we study this a little bit more concretely? So we can characterize the scale of this system by blowing up each pixels in this figure. So we can see at finer scales, we can still see the A's are here, but gradually at the intermediate scale, these A's are becoming blobs and they form a big B. And at very large scales, the holes in B's are filled in and you just have one single blob. So these are called the connected components when they're connected together, and these holes are called loops. So we can look at the loops and connected components in these series of structures to figure out how the system is scale dependent. For example, the loops, the smaller loops in A, only presents at smaller scale. We may be able to draw these, represent these loops as little bars at which scales they're present. And the loops in B's, however, they're only present in larger scales. And both of them disappear at even larger scales. So with this collection of bars, we can call them a bar code. And they gave a multi-scale topological portraits of this particular figure that I showed you. And there is a precise mathematical tool to let you do that. It's called persistemology, which I didn't show at the beginning because I think it's scary when I first time saw it. But this is the essence of what persistemology really is. Now we apply this, study the recurrence of these bar codes for the 3-agent example. Now we can see this is the recurrence of the connected components, meaning if these points are actually connected, we see there are it highlights 3 sudden changes that actually indicates the transition between the escape from this all in phase pattern. And the recurrence of loops in their barcodes highlights the point at which they enter into this 3 recurrent patterns and when they leave this particular pattern. So overall, it captures what we already know about the 3-person interaction. Well, now we're going to see if it works for the 8-person. The first thing you can see is that there are a lot of structures in the recurrence of these topological features compared to what I showed you before. And this recurrence of connecting components highlights there is a sudden change around 30 seconds. When I first saw this, I was really confused. I was like, I saw nothing here. Like, this must be an artifact. So I spent a little bit more time looking at the dynamics. So I see, well, what's happening before 30 seconds? Before 30 seconds, these 8 oscillators now show as their frequency dynamics. There are 3 pairs of them: the orange-red, the green-blue, and the purple-blue, another blue sign. And there is a lone wolf on top, and there is a yellow guy that's oscillating between them. But at 30 seconds, there is a sudden regrouping of these 3 pairs and this yellow guy. It means that these 3 pairs broke up, 2 of them broke up, and this blue guy rejoined the group on lower level, and these 2 from different group pairs before regrouped together, and the top 2 regrouped together. And after this transient, they return to their early partners. So is this just a random bumps in the data? After I look at the relative phase corresponding to this period of dynamic, I think not. Because the duration of this partner exchange dynamics is controlled precisely by the relative phase between the yellow and orange oscillator. It takes exactly time for the system to be destabilized from antiphase and go back to antiphase. So it's a local perturbation on this particular relative phase and cause an avalanche of repartner in the collective dynamics. So by using topological analysis, I was able to show an important collective pattern transition that was not be able to observe by traditional means. So to conclude, I showed you a new experimental paradigm for studying coordination dynamics among multiple agents, where I can manipulate their frequencies and can manipulate their coupling. And this experiment revealed the coordination patterns among multiple spatial temporal scales, and I was able to capture them with a theoretical model. And this model happens to connect to important theories of large-scale and small-scale coordination dynamics. And I also find a critical parameters that connects the emergence of behavioral complexity across multiple scales. And then I showed you how to think about complex metastable pattern emerged observed in the experiment and the model through topological classification. And finally, I showed you how to use topological data analysis to construct topological portraits across multiple scales and detect important transitions in the single trial dynamics. So what next? So why am I here? So I'm trying to look at if these complex, these principles of generating complex coordination pattern can help us understand neurodynamics. So as Plato has said, if you can automatically substitute any justice in this paragraph with complexity, Socrates/Plato said, when we're lacking keen eyesight, we were told to read really small letters, like in the brain, from a distance. And then we notice the same letter exists elsewhere in a larger size, on a larger surface. We consider it a godsend, I think, to be allowed to read the larger ones first and then to examine the smaller ones to see whether they're really the same. There is the justice of a single man and also the justice of a whole city. And if a city is larger than a single, and the city is larger than a single man, let's first find out what sort of things justice is in the city, and afterwards we look for it in the individual, observing the way in which the smaller is similar to the larger one. And so I want to acknowledge, and these are my committee members, and the fundings were coming from NIH. And now I'm open for questions. And this is the actual photo of the actual equipment that I built.
So in these experiments, do people see the same flashing lights that everyone sees? Or do they have different flashing lights?
During the metronome pacing period, they have different flashing lights.
So their individual light is different, I understand that. But what about the other 7? Are they seeing, you're showing each of them 8 lights? Or
Yes.
one light?
I show them A lights. So each one have A lights. The 8 of them have 64 lights.
Oh, and so those 8 lights might be different.
Exactly. A lights are different.
Okay, so my question is in that was when you were comparing the model to the data,
Mhm.
If I understand, the model is deterministic.
Yes.
Right? So the variation from all those points from your data, is that just noise or is there other systematic variation?
Yeah, that's a good question. So I want to go back to
The way of the bills.
one of the There are too many slides here. So yeah, this on the right-hand side, this is deterministic.
Those points are the data points?
The points are the data points. So the variation here, well, I can add noise in it, and then it will become noisier. But the main variation here was actually coming from metastable coordination. So it's because it never actually becomes synchronized, that gives them the freedom to exhibit a range of behavior. And that's one of what I think is the most important thing to think about complex system as metastable patterns, because they are both coordinating while they're not losing their individual differences. And that gives you the variability.
Are these points all from the model?
Yeah, these are all from the model.
So
These are
from different initial conditions.
Yeah, random initial conditions. Yeah.
So from a sort of perspective of cognitive science, you have people who are doing a task, and you might want to ask, like, what's going on in their heads that might be giving rise to these dynamics. And I kind of thought it was interesting, kind of a pure time perception task, essentially, which is to just like try to keep a consistent pace.
Yeah.
So like actually the optimal solution for that task would be to close their eyes and ignore the dots on the screen, right? But
Now I asked them to look at the center of the LED array because I don't want them to coordinate, but I want them to be influenced by other people's.
right, so it's sort of an interesting task because there's sort of like a pure time perception task where they just are, if you incentivize them for like getting as close to the thing as possible, then they would probably stop trying to attend to the dots. But if you incentivize them for coordinating, then they would also probably act differently. And by mixing them together, I kind of wonder whether there's like a mixture model that you could use where you combine sort of like everything we know about human time perception, which is that it's like how particular biases, and also like attention processes essentially, where like we know that the short-term like visuospatial sketchpad like can't contain 8 things simultaneously, really.
Right.
So like if they're applying covert attention to like subpopulations, you might see that some of these phase switches correspond, like if you were eye tracking them, well, they weren't allowed to fixate on the individual dots, but like they might correspond to shifts in covert attention.
Right. So there is I would say, I think there's multiple questions in that question. So there is a question of what is attention in this particular task. So if I just want to go back to the so is attention arising from is sort of a illusion that emerged from the actual coordination, or it was intentionally being, a result of, oh, I'm actually actively paying more attention regardless of the this actual patterns. It might be difficult to differentiate. So I interviewed a lot of subjects. The most common reaction was, well, those are other people? So I told them, well, after the metronome disappeared, they will see other lights flashing. And all they need to do is look at the center of the LED and keep tapping. So a lot of them actually didn't realize where those dots or flashes were coming from, the people, or I just try to throw them off with random flashings. So they didn't actually know it was very social. And if you do the experiment yourself, you will be sort of automatically attracted to some of the patterns. If I showed you this, come on. Yeah, if you look at this long enough in a dark room, you will start to, even if you don't shift your eyes, you will start to sort of pay attention to other people, some people more. It could be that some people are synchronizing with you. You might be able to pay attention to synchronized patterns between different oscillators, different flashes. Or in some other cases, we call there's a mutant fireflies. So there will be people tapping extremely fast, and they don't know it. So it's definitely a complicated situation if we consider all the cognitive processes are actually involved. But I think what is really interesting about it is in the model, I really just assume there are simple phase oscillator with a natural frequency. And that's enough for it to work. And I think that was kind of surprising to myself as well, that I don't need to assume what exactly was the cognitive process, the underlying timing principles, but the coordination between them sort of transcend the specific processes that may underlie the timing.
Can you call it coordination though? Because actually they are not us, or they don't know that they are coordinating. In human behavior, oftentimes, there are intention of coordination, right? Yeah. So here, actually, it's not really. I don't know whether you can manipulate that. Like in one condition, you just instruct the participants and also incentivize them. Say, okay, you please coordinate as much as possible, and we'll pay you more if you can do a good job. And versus, don't tell them and see whether there are different patterns.
Right. So that has to go back to my earlier motivation, where I was thinking more about, what is the secret of life, and how is a human organism is similar to social organism. We might feel a lot of intention on a social level when we're doing stuff, but what is the intention for a molecule? If I am mitochondria, I'm doing a lot of things. Am I intentionally organizing the energy supply of the cell? If I'm a protein and I triggered a DNA duplication, am I intentionally doing that? So do you think all the cells in the body are coordinating, and do you think they're intentionally coordinating? So that's, how I think about it, and the reason why I designed an experiment that way. I was sort of like, I don't quite want to tell you what to do. I want to see what you naturally do without that much intention. They may have like spontaneous emotion emerge during the task. Some of them are more social, I would say. They may have their own theories about what they should do, like they do. I interview some of them. I say, this is my instruction. Why are you thinking about a different task? They were like, I thought this is what you meant. I was like, I didn't mean it. But they do have their own internal models of, their own intentions in this. But I just didn't interfere with that. Yeah.
So they were tapping slightly faster than 1 hertz?
They were ranging from 1.2 to 1.8 hertz.
Okay, so they're going to hear like 14 taps in 10 seconds or something. And then there's 3 seconds where there's no tapping. And then they're just being asked to continue for 50 seconds.
Yeah.
I'm just surprised that anyone, even subliminally, remains in sync. Because I feel like even if we had to count 1 hertz counts, like a true second, I feel like with our eyes closed or not knowing what pattern, or that the fact that it's the people who are across from you or something, like you're not looking at the body language of the person next to you or something, it's just surprising that anyone stays in sync quantitatively.
Stays in sync?
That you would even have phase or antiphase relationships, because some people would be drifting. The 1.2 hertz person is just drifting slow, the other person's drifting fast. Even if people are converging back to the true frequency, then they would just be like, it's just a lot of subliminal information to be parsing out.
Right. It's not they're going back to the metronome frequency. They're simply attracted to other people.
But they know to be attracted to, like when you do when you said they're out of phase by 0 hertz, 0.3 hertz, or 0.6 hertz, so they're offset in their starting position?
Yes.
By 0.3?
So I randomly assign their metronome. When I say they were assigned the same metronome. It was oversimplification to keep your attention right within 1 hour. So I actually assigned, there are actually different metronomes. They're all the same frequency but random initial phase. So they started off non-near in phase and antiphase in general.
They just have the 0.3 seconds starting, even 45 seconds later.
Oh, during the 0.3 seconds, they were continuous tapping, but they don't see other people. They were tapping by themselves, and then suddenly they see a bunch of dots flashing, and they try to continue to tap at that frequency. And they just
don't know whether it was a metronome to begin with, or when they see it again, that they could think it's the metronome.
yeah, they don't know if I was messing with them or not. Some of them said thought I was messing.
Blinky or something.
Yeah.
Yeah.
So if you go back to the animation that you just had up, when I watch that, as well as the individual light flashing, I can't help but sometimes see what looks like a rotation around the circle.
Yeah.
And that is, at also a frequency which I would want to entrain to, and it would shift.
Yeah.
So did you look at that at all? Is there any effect of the order of how the lights are positioned? And
Right. So distribution-wise, these patterns are relatively rare, actually. So they mainly show up when the so what I'm trying to say is statistically cannot say if this is for sure, because there are very few trials where they actually manage to have this some kind of what we call splay state when they follow one another. And this case is when there are pace all with the same frequency, so their frequency has to be close enough. When they're having a splay state, they has to be sort of phase locked. Their frequency has to be very close. So it's kind of a rare event if look at in aggregate. Yes.
So following on front row guy's question, they were sitting around a table, and so they had both the display to look at, but there was also this audio information floating around. Do you think there would be any difference if you had them like more isolated?
So I played noise in the background to prevent them from hearing each other. But this experiment actually have a second part where I split them because I told you I can control the network connectivity between them. So I actually split them to two separate groups. And I found out they were still coordinating because they can still hear. Sometimes it's just one person tapped really loud in one experiment will destroy our entire data. And I didn't have enough trials to wash off that one person tapping really loud, which happened to be, I shouldn't talk about the privacy of the subjects. But yeah, there are people who does tap really loud. Ideally, I would sort of give them headphones, with headphones that's playing noise. That would be a little bit better. So yeah. Because auditory coordination is much stronger for humans than the visual coordination shown here. But
particularly for rhythmic.
Yes. And we're also very constrained with lab space. But yeah.
Practicalities of human subjects.
Yeah.
Or online, just do a mechanical turn.
So the reason that I did this, I actually spent, I would say, how many times? I spent 2 years on this. So this thing itself took 2 years to set up. Probably never going to be able to do at Stanford because everyone seems to want to have a faster progress on things. But the reason I had to spend 2 years on this is like I was doing electrical engineering of this apparatus. The reason it's very hard to do online is that rhythmic coordination is very sensitive to delay. 5 milliseconds delay is good enough to have an effect, and coordination pattern itself is dependent on the delay. If you have longer delay, you will have self-to-self coupling. You will have a different pattern with yourself. You have 2-to-1, all different sort of stuff when you start to have too much delay in the system. So the delay here is really critical. And now I'm inputting 8 channels of data into the computer. Well, I need to do a complicated transformation when I incorporate information of the spatial maps, that what they see really spatially located on the LED array. I need to do the network connectivity stuff. I also need to compute the metronome, etc. in the middle. And I need to redistribute 64 different channels out to these subjects. And we explored a lot of preparatory hardware to do that. First of all, they don't really give you the instrument to control 64 bits of output very flexibly. And so I was doing a lot of microcontroller stuff for this equipment. There are 2 microcontrollers on one PC in this, a lot of soldering. I designed these touchpads myself, so to really lower the latency of the delay onto 2 to 4 milliseconds. So that's the reason why you cannot do this online. It will be too slow.
So on the point of the latency, it's cool that you're able to control the response latency that well, but there's so much variability in human response latency, just variability among different people in their response times.
Yeah.
Given the same stimulus.
Yeah.
I wonder, I guess it kind of goes back to the question of what is the mechanism, the cognitive mechanism, through which people's responses are being affected by their visual information, because different participants are going to have different processing time
Right.
to initiate their motor actions.
Right. So you're talking about how the individual differences are coming into play. So in the model actually fitted the individual distribution of frequencies during that short 3-second period where they're not seeing other people, but they have already been paced. So they have a 3 seconds recording of no social interaction and already been paced. So the diversity there is large, but that's not the diversity I'm trying to explain. I'm trying to explain, given the diversity, how do they coordinate? So I was sort of taking that as a given. No matter what is the mechanism, it could be a degenerate problem. It means for a given individual difference, there can be infinitely many ways that this person can be different from another behaviorally. There doesn't have to be a unique way. For example, if this person has a longer finger, if this person has a response time. So there's a multiple, I would say, knobs in the system that you can tweak, and that will eventually generate some diversity in how they respond to the metronomes and how they keep track of time over time. And these were incorporated by fitting the subject distributions of natural frequencies. It was not incorporated in the other noise terms, but what?
If you ran it on mechanical Turk, you could fit that.
I
in the
could.
same way.
Yeah. The latency wouldn't be
wash
same.
out.
Because it's constant for a particular keyboard or whatever.
Right. The constant is not enough. It just has to be short enough. So it's because it's a closed loop system, is when you tap, it does a lot of processing and the signal return to you, and that has to be short enough. You cannot tap and don't feel like this is your own tap. That's flashing. This will cause really confusion on the subject's perspective.
Do you tell them that one of the lights is their tap?
Yes, I told them.
They know that.
Yeah. Sometimes they still forgot. They're just, yes.
So this methodology could be a question altogether. Economical interactions in the marketplace, and if you did apply, do you think you would get closer to John Maynard-Keynes model, or maybe von Mises model?
I have no idea.
Oh, you don't know.
Yeah,
One is more top-down
yeah,
entrainment, and one is more bottom-up.
That's an interesting question.
Yeah.
yeah. I have no idea.
I think.
Sorry, that's an uninteresting answer.
Unrelated question. Can we do statistics on persistent homology? So you showed even when there was 8 traces, it was still 1 to 3, 4 to 5, 6 to 8. So it was only 8 out of the 8 times 7 plus 7 plus 6 plus 5 plus 4. So when you plot them all, can you ask, is there a bootstrappable distribution of synchrony, or is it just always possible to subset the 50 all pairwise interactions down to 3 that have really specific dynamics?
So what I was trying to explain that I took out one of the slides because I want to manage your attention. So here is another slide to explain why I did what I did. To analyze the topological patterns in the frequency. I showed you there's a part at the end that I showed you the frequency, using the frequency dynamics to show the coordination patterns. And here I show you why that's important. So metastable phase dynamics, this is A here, is the relative phase between two oscillators. When their dual is kind of flat and then escape, and the dual again is flat again and then escape, like this. And this information, the reason we study the characteristic dynamics of metastable coordination are the dual escape dynamics. And these can be precisely reflected in the frequency dynamics. So when they're dueling, these curves are closed or forming sort of one connected component. And during their escape, they sort of forming one loop. And why is that? This is actually because the frequency here is a derivative of the individual oscillator's phase. So relative phase is the integral of the the relative phase is the integral of the difference between frequencies. So that is to say, because they always duel at in-phase or antiphase, so if they go away from in-phase and go back to in-phase, that's going to give you a 2 pi. And that corresponding to the size of this loop or area between these curves to be 1. So there are some quantum effects in here. So the size of these topological structures and the fact there are loops and connected components is characterizing. These topological structures characterize the key dynamics in metastable coordination. And in multi-agent case, the pattern can be much more complex. And this, looking at the frequency dynamics itself, gives you a really a short way to reduce a high-dimensional dynamic problem to a 2D geometric problem. So it's mathematically, we can really only analyze the topological structure across scales in a 2D graph, but we know all the dual and escape dynamics of the relative phase, even though we don't know which phase they're dueling at, but we know when they're dueling and after how long of a phase they return to the same pattern. So yeah, I have a lot more slides, so I was like really hiding everything.
Any other questions?
Are these papers, they're not available yet, right?
Most of the papers are, the experiment was published, and the model is on archive, which is very, very difficult to publish, to be honest, because it's very offensive. If you Google Kuramoto model, and you will understand why people don't like an article to say, oh, Kuramoto model is probably insufficient to characterize experimental data. And so it's kind of offending for a lot of people. Delete this clip from the topological analysis here is going to come out on archive pretty soon, hopefully. I'm waiting for a mathematician colleagues who, they're not easily socially coerced. So I can only say, take your time, don't worry about it. I think my favorite part of the 3 oscillator use winding numbers to characterize 3 oscillator dynamics is only in my dissertation, which is also freely available online. But it might not be published ever because I start running out of time when I moved to Stanford. Yeah.
Do the models give you some idea of what other interesting things might happen with larger groups? So you did n equals 8.
Right.
So whether it would predict new interesting behaviors at larger sizes?
So right now, we only know that at larger scale, you have more stable patterns. That's one thing that we can predict. Of course, at larger scale, you can, in principle, produce more complex metastable patterns. But I think the most important step for metastability was from 2 to 3. So from 2 oscillator problem to 3 oscillator problem, that gives you all the infinitely many possible patterns. And you can become more infinitely many when you're going to larger scales, but the qualitative change from one metastable pattern to infinitely many, I think, is the most interesting thing.
So I was just wondering if you're like, somehow you become part of a big group and you see lots of things flashing, that maybe that would keep you more entrained than if you just see 1 or 2. I mean, that's just a guess.
Yeah, so you can think about this. That is one of the effects. So I'm going to go back to the model. So there is actually a difference between my model and the Kuramoto model, even though I said they're the same when we remove the second order coupling. So you will see here I have a coupling strength A outside the sum. In Kuramoto model, it has a K, a coupling strength, over N. So you can imagine that their coupling strength was normalized by the numbers of oscillators. So the behavior of the Kuramoto model does not really change too much with the numbers of N due to the normalization. But the behavior of this model will change because you can imagine you just times N here from this model. So it's equivalent to Kuramoto model as increasing the K by not normalizing by N. So in large scale, it will definitely turn to be more synchronized because the effectively increase of coupling strength.
Actually, I think your analysis of intergroup integration versus segregation was very interesting. It reminded me of a paper that published in PNAS on financial investment. So they looked at whether the stock market is composed of people who are homogeneous, relatively speaking, for example, or you know that all the investors are from your own ethnic group versus you know that some investors are from another ethnic groups. And then they look at the efficiency of the stock market and when it will burst, you know, in terms of price. And what they find is that with more diversity, actually it's less likely to burst and it's more efficient, yeah, in a way. So I think it's very interesting in your analysis. Actually, it's in the middle level that it has integration. If it's too diverse, then it has segregation, right? Yeah.
Yes.
Now, in your definition of diversity, actually, you define in terms of the Hertz difference.
Yes.
And frequency difference.
Yes.
What if diversity is defined as multiple groups? You know, multiple different groups.
Right.
So you can have 3 different like frequency group or 4 different frequency group. What do you think? Would the same kind of mechanism occur?
So their frequency diversity, I still divide them into 2 frequency groups. So in principle, I can use the same experiment to divide it into at least 4.
Right.
3 is a little bit difficult because you're not going to have integers of the equal size groups. So I do not imagine the results going to be very different.
Really? Actually, in human behaviors, actually,
I mean, in the model, I do not expect the model.
But I think it's interesting because in human societies, many, you know, there were studies that show if you have 2 sizable different groups, they're more likely to have more conflict. So actually, segregation is more likely to occur. But if you have multiple groups, you know, but relatively smaller size than, you know, the 2 big groups, then you're more likely to have integration.
Well, it depends on a lot of things.
Right, that's true too, yeah.
It depends on if they actually coordinate, right? For example, I would say in southern China, there are many more subcultures, ethnic groups in South China. It doesn't mean that are highly integrated than in northern cities when there are less ethnic groups.
Actually, that's the case. I mean, in China, for example, if you go to southern China, like Yunnan have really a lot of ethnic groups, and then the ethnic groups are much smaller in size, and in terms of intergroup relations, actually it's much better than, for example, go to Tibet or Xinjiang, where they have more sizable group, but there are fewer of them. Yeah, there were research that shown that, yeah, actually, in those areas, there are more intense intergroup conflicts. Because there is easier to see a fault line. So it's easier to see in-group versus out-group. But then when you have really multiple groups and they're smaller in size, then that might not necessarily, or there might be other things that help you to re-characterize. So it's a matter of characterization, and re-characterization.
As I said, it depends on if they actually interact or not. Mm-hmm. If it's a small group, but they're localized, they don't really interact with the outside world, I wouldn't say a region with multiple smaller groups will actually be more integrated if they don't actually interact. But if they interact, yes, maybe. So for example, in the simulation that I actually showed one other simulation. Come on. This is one my advisor's favorite plot. Is this one. So this is a uniformly coupled 8 people, and they're starting with slightly different equally. So this simulation, actually, there's no group. So each individual has their own intrinsic frequencies, and there is no group here. So their dynamics is relatively interesting. So for each period, they started off branching off. There are 8 separate groups at the beginning. But at the end of this period, they started to segregate into 3 different groups and become 2 groups at last and become 1 group again. So, I mean, it's also a dynamical processes. You cannot say they are integrated and then they will be forever integrated, but it can be, they can regroup and do all different sorts of things over time. But this particular one is more diverse. You can think of it as 8 different frequency groups.
Okay, let's